Okay. Good morning, everyone. Good morning, ma'am. I am from Group 8. We're gonna presenting our presentation, and the topic is about vector. So the member of Group 8, there is Naila Fauzia with name 13056230008. Nadira Hasna Box with name 13056230056, and also myself, Cindy Fiona Luciana Simatupang, with name 13056230026. So we have a few topics what will we learn today. So today we're gonna learn about the definition of vector, the notation of vector, similarity of vector, vector negative, zero vector, the science of population, operation in vector, norm of vector, vector distance, vector in two spaces, vector in three spaces, unit vector, vector multiplication with scalar, scalar multiplication of two vector. So first, what is the definition of vector? Vector is a quantity that has both magnitude or length and direction. Vector are used in various fields such as physics, engineering, computer graphics, and more. In mathematics, vector and scalar are fundamental concepts used to represent and manipulate quantities. A scalar is a quantity that only has magnitude and no direction. Scalar can be real numbers such as 3, minus 2.5, or pi. They are often used to represent quantities like temperature, mass, time, or speed, where the direction is not relevant. So, the difference between a scalar and a vector is a vector quantity has a direction and a magnitude, while a scalar only has magnitude. A vector is the redirected line segment, whose line is magnitude of the vector and with an arrow indication the direction. The direction of vector is from its initial point or tail to its terminal point or head. As you can see, there is a picture. So on the left, there is tail, direction, and head, and that all holds magnitude. And on the right is initial point to terminal point. So how we write the notation of vector? Vector are typically represented in boldface, like phi in lowercase or phi in uppercase, or with an arrow on top or italics. In a coordinate system, vectors are commonly expressed in component form into spaces. Vector phi is written as vector phi is equals phi1 and phi2, where phi1 and phi2 are the components of the vector along x-axis and y-axis. And in three spaces, a vector phi is written as vector phi is equals phi1, phi2, and phi3, where phi1, phi2, and phi3 are the components along the x, y, and z axis. Another way to express a vector is in terms of its unit vector along the coordinate axis, such as I, j, and k for three spaces. And for writing the price of the vector is written the magnitude of vector is shown by two vertical bars on either side of vector, or it also can be written with double vertical bars. Example, vector value vector A is written with one vertical bar vector A or double vertical bar vector A. So next is similarity of two vector. The vector can be said be the same if both vectors have the same magnitude or length and direction. Also, two vectors are said to be not the same if both vectors have the same value but different direction. Both vectors have different value but the direction is the same. Both vectors have different value and the different direction. For more details, we can see the image. That is vector A, vector B, vector C, vector D, and vector E. The vector value of A, B, C, and D are equal in size. The vector of vector E is smaller than the other four vectors. From the picture, it can be concluded that vector A equals vector C because the value and the direction are both the same. Vector A and minus vector B, sorry, vector A is equals minus vector B because the value is the same, but the direction is the opposite. Vector A is not equals to vector D because the value is the same, but the direction is different. And vector D is not equals to vector E because the value and the direction are different. Next is vector negative. The negative of vector with the same magnitude as the given vector, but in the opposite direction. It is obtained by multiplying the given vector by minus 1. The negative of vector and the given vector are exactly in the opposite direction. As you can see, there is the image of vector AB and vector BA in opposite direction. So the negative of vector AB is a vector that is obtained by multiplying it with minus 1. The negative of vector AB is the minus vector BA. So AB and minus BA are the same magnitude but in opposite direction. So norm of vector AB is equals norm of vector BA, but they have opposite direction.
Okay, next is zero vector. Zero vector is a vector that has zero length and whose components are all zero, often denoted as zero or zero vector. As we can see in the picture, there is the difference between the vector. There's a vector A and zero vector that is no have no length or components are all zero.
So next we have the signs of equation. For any vector u, v, and w, and any scalar a, b, the following relationship hold. First, u plus v is equals v plus u. The sum of u plus v is added to w is equals u plus the sum of v plus w. U plus 0 is equals 0 plus u equals u. U plus u is added to minus u is equals 0. K is multiplying by the product of L multiplying by u is equals the product of K multiplied by L is multiplying by u. The sum of u plus v is multiplied by K is equals K multiplied by u plus K multiplied by v. The sum of K is added to L is multiplying by u equals K multiplying by u plus L multiplying by u, and 1u is equals u, and norm of a u is equals absolute A is multiplying by the norm of vector u.
Okay, the next is about the operation and factor. So this is the first one is addition. So it's given two factor, it's vector A and B. We form their sum A plus B as follows. We translate vector B until its tail uh, coincides with the head of A. Then the directed line segment from the tail of vector A to the head of vector B is a vector A plus E. So this is we have the law additions. The commutative law states the order of addition doesn't matter. This law is called the parallelogram law that vector A plus vector B is equivalent to the sum of vector B plus vector A. Next. Okay, next it's subtractions. As explained earlier about the negative factors, we define the fractions. We define the factor minus a, which is the opposite of a. Factor minus a is a vector with the same magnitude as a but in the opposite directions. We also can define subtractions as addition with the opposite of the factor. So this is factor a minus factor b is equivalent to factor a plus negative factor b. So we have the example. The first one is find the addition of factor PQ and QR, where PQ is 3, 4, and QR is 2, 6. So PQ plus QR is 3 plus 2 and 4 plus 6. So the solutions, the addition of the factor PQ and QR is 5 then. The number 2 is if factor A, it's 4 minus 2 and 3, and B, it's 1 minus 2 and 5, then find factor A minus factor B. So the solution is 4 minus 1 minus 2, negative 2 minus negative 2, 3 minus 6. So the solution of factor A minus factor B is 3, 0, and negative 2.
So next, we have a norm of a vector. We will denote the length of a vector x by the symbol two vertical bars on each side of vector x, which is read as the norm of vector x. It follows from the theorem of Pythagoras that the norm of a vector x1 and x2 in two spaces is the follows is the graphic on the left. There is x-axis and y-axis, and there is a line as x1 and x2. This follows from the theorem of Pythagoras that the norm of a vector x1 and x2 in two spaces is norm x is equals the square root of the sum of x1 square plus x2 square. Similarly, for the vector in three spaces, x, y, and z, it follows from two application of the theorem of Pythagoras that there is a x, y, and z axis, and there is a line py, px, and pz, sorry, and there is a line vector phi, x, y, z. So the norm of vector phi is the square root of the sum of x squared plus y squared plus z squared.
Okay, next is vector distance. If P1 and P2 are points in two spaces or three spaces, then the length of the vector P1 and P2 is equals to the distance d between the 2 points. Specifically, if P1 is x1, y1 and P2 is x2, y2 are points in two spaces, then the formula is distance d if distance d equals to the length of the vector P1, P2 equals to square root of the sum of x2 minus x1 square added to y2 minus y1 square. This is the familiar distance formula from analytic geometry. Similarly, the distance between the points P1 are x1, y1, and z1, and p2 are x2, y2, and z2 in three spaces can be formulated as distance d equals to the length of the vector p1, p2 equals to square root of the sum of x2 minus x1 square added to y2 minus y1 square added to z2 and z1 square. There is an example here. Number 1, given vectors A, 6 and 2, and vectors B, 2 and -1, calculate the distance between these vectors. So the answer, as we know from the previous slide, there is a formula. So we got 2 minus 6 square plus negative 1 minus 2 square, the equals to square root of negative 4 square plus negative 3 square, and we got square root of 16 plus 9 and square root of 25. So the result is 5. So the distance between vector A and vector B is 5. Next is vector into spaces. The length of the line segment representing the vector. Vector lengths, or we can call it the norm of a vector, as norm of a vector V equals to square root of V1 square plus V2 square. As we can see on the right pictures, vectors can be presented as linear combinations of base vectors. For example, vector I is 1 and 0, and vector J is 0 and 1. So the following is vector V equals to V1 and V2. So we got V1 multiplied by 1, 0 plus V2 multiplied by 0, 1. Then the result is vector V equals to V1 vector I plus V2 multiplied by vector J. The next is vector in three spaces. Vectors on three-dimensional space are x, y, z. The distance between two vectors points in three spaces can be determined by developing the Pythagorean formula. If A are x1, y1, and z1, and B is x2, y2, z2, then the length of AB is the length of vector AB is square root of x2 minus x1 square plus y2 minus y1 square plus z2 minus z1 square. Vectors can also be presented as linear combinations of base vectors. For example, vector I is 1, 0, 0, vector J is 0, 1, 0, and vector K are 0, 0, 1. So the following is vector V equals to V1, V2, and V3. So we got V1 multiplied by 0, 1, 1, V1 multiplied by 1, 0, 0, plus V2 multiplied by 0, 1, 0, plus V3 multiplied by 0, 0, 1. So the result is vector V equals to V1 vector I plus V2 vector J plus V3 vector K. Next is vector addition and subtraction in three spaces. Adding algebraic vectors can be done by summing the components of the layout if vector A is A1, A2, and vector B is B1 and B2. Then the vector A added to vector B equals to A1 added to B1, A2 added to B2. Vectors reductions or subtraction applies the same as the sum. So we got vector A minus vector B equals to A1 minus B1 and A2 minus B2. Next, vector addition and subtraction in three spaces. The addition and subtraction of vectors in three spaces are the same as vectors in two spaces. So we got vector A multiplied by vector A plus vector B is equals to A1, A2, A3 added to B1, B2, B3 equals to A1 plus B1, A2 plus B2, and A3 plus B3. For the subtraction, vector A minus vector B equals to A1, A2, A3 minus B1, B2, B3 equals to A1 minus B1, A2 minus B2, and A3 minus B3. Next. There's an example here. Number 1, if vector U are 5 and minus 3, and vector v are 7 and 10, then the result of vector u minus vector b is 5 minus 7 and negative 3 minus 10, so we got minus 2 and minus 13. For number 2, if vector A are 9, negative 1, and negative 4, and vector B is 12, 0, and negative 5, then the result of vector A plus vector B is 9 plus 12, negative 1 plus 0, negative 4 plus negative 5. So the result is 21, negative 1, and negative 9. Next is vector multiplication with scalar. A vector can be multiplied by a scalar or a real number and will produce a new vector. If v is a vector and k is a scalar, then the vector multiplication can be written by k multiplied by vector v. An algebraic vector multiplication in two spaces can be formulated as k multiplied by vector v equals to k multiplied by v1 and k multiplied by v2. Or the vector multiplication into spaces can be formulated as k multiplied by vector v equals to k multiplied by v1 and k multiplied by v2 and k multiplied by v3. Here are some kinds of scalar product of k and vector v if multiplication k multiplied by vector v. If k is more than 0, then the result vector is in the same direction as vector v. If k less than 0, then the result vector is opposite to the vector v. If k is equal to 1, then the result vector is equal to the vector v. If k equals to 0, then it produces a zero vector.
So next is a unit vector. So a vector from a norm one, it's called unit vector. Such vector is useful for specifying a direction when line is not relevant to the problem at hand. You can obtain a unit vector in a desired direction by choosing any non-zero vector v in that direction and multiplying v by the reciprocal of its length. So more generally, if v is any non-zero vector in Rn, then a vector u is equivalent to 1 over the norm of phi multiplied by a vector phi that is in the same directions as phi. The process of multiplying a non-zero vector by the reciprocal of its length to obtain a unit vector is called normalizing phi. So this is the example of the normalizing a vector. So find the unit vector u that has the same direction as phi, 4 minus negative 3. So u is equivalent to phi over the norm of vector phi. So solve the vector u, it's 4 over 5 and negative 3 over 5. Next. So next, it's about the scalar multiplication of two vectors. The first one is about the dot product. So the scalar multiplication of two vectors, it's also called the product of the columns, and it's written as vector A dot vector B. So the scalar problem of vector A and B, it's done by multiplying the length of the vector A and the length of the vector B by cosinus theta. Angle theta, which is the angle between vector A, vector, and vector. So we can see in the right image, it has a vector A and vector B. And the theta, it's the angle between the vector A and vector B. So vector A dot vector B is equivalent to the norm of vector A. The norm of vector B, it's multiplied by cos theta, or cos theta is equivalent to vector A dot vector B over the norm of vector A multiplied by the norm of vector B. Also, the dot product, it's can using the concept of multiplication of each element. Suppose there are two vectors and the dot product can be calculated by dot A, vector A dot vector B equivalent to A1 B1 plus A2 B2 and A3 B3, where theta is the angle between the vector A and B. So if the vector A and vector B is perpendicular to each other, so the theta is equivalent to 90 degrees, then we get a vector A, the vector B is equivalent to 0. If the two vector A and B are parallel to each other, so the theta is 0 degrees, then we get vector A, the vector B is equivalent to vector A and vector B. So this is also has the properties of the product. Next, the next one is the cross product. So the easiest way to define cross product is to use the standard unit vector I, J, and K for the R3. If U is U1, U2, U3, and the phi is phi1, phi2, phi3, then the vector U multiplied by vector phi is defined as U multiplied by phi, so U2, U3 minus U3 V2 multiplied by I plus U3 phi1 minus U2 phi3, it's multiplied by J, and plus U1 phi2 minus U2 phi1 multiplied by K, which is much easier to remember when you write it as a determinant. Next. Next is properties of cross product. There's a whole lot of properties that follow from these definitions. First of all, is anti-communicative, that vector U multiplied by vector U, it's equivalent to negative the sum of vector U multiplied by vector B. So any vector crossing itself is 0. So vector V multiplied by vector V is equivalent to 0. So is it linear? Then that is linear in each argument. So it distributes over addition and subtraction. 0 could add as 0, and you can pass scalar in and out arguments. So this is the distributive properties for cross product of the zero factor and multiplication by a constant. So this is the exercise. If there's any question.
Okay, thank you for the good presentation. Yeah. Before we are going to the exercise, for all the students, have you any question for this group about the explanation about factor? Is it clear enough for you? Please tell us, yeah.
I think it's clear enough, ma'am.
Clear enough. Okay. If it is clear enough for all of you, maybe we can go to the next agenda, that is discussion, yeah. There are four questions. Number one is about the distance between two vectors, and number two, okay, about the operation, yeah, of the vector, and number three, it is like an application, yeah, of the vector in the apa tuh, bidang datar tuh, ya. And then number four, you have to find the value of the variable x. Okay, you can try it, and if you want to try for what number, you can submit or upload, yeah, your answer to the group, and you can explain your answer to the class.
And for the group presentation, please tell your friend, is it wrong or it is correct, or maybe something revised, something have to be revised ya. Ditunggu ya, mungkin tiap soal berapa ya? 3 sampai 5 menit ya. You can choose one, number 1, or maybe number 2 first, or number 3, or number 4. In exercise, vector A is equal to 2e plus 3j minus 5k, and vector B is equal to minus 4e plus 7j plus k. Then the result of vector where vector C is equal to 3 multiplied by vector A minus vector B. Vector A is multiplied by 3, 3 multiplied by 2, 3 multiplied by 3, 3 multiplied by minus 5. Then the result is 6e plus 9j plus minus 15k. And vector C is equal to 3 multiplied by vector A minus vector B is 6 minus 4 is 10. 9 minus 7 is 2. Minus 15 minus 1 is minus 16. Then the result for number 2 is 10e plus vector C is equal to 10e plus 2j minus 16k. Is the answer is correct?
Okay, but the answer is correct.
Okay, the group say that the answer is correct. How about the others? Do you think the same? Is it correct?
Yes, ma'am, it's correct.
Correct. The other students? Do you agree?
Yes, ma'am, I agree.
Okay. Okay, 3 question remaining ya. Number 1, 3, and 4. Okay, Samuel wants to answer number 4, please, Samuel.
Okay. So from the question, we got vector A equals to 3, 1, and 2, and vector B equals to -2, 4, and x, and they both perpendicular. Then I want to find the value of x. So that since A and B is perpendicular, so the dot product of both vectors is equal to 0. So this is A dot B equals -3, 1, 2 times -2, 4, and x equal to 0. And we multiply the same elements from those vectors. -3 times -2 plus 1 times 4 and 2 times x equals 0. -3 times -2 is equal to 6, and 1 times 4 is equal to 4, and 2 times x is equal to 2x equals to 0. So we added the 6 and 4 equal 10, and we added 10 to 2x equals 0. So we subtracted both sides with 2x. We got 10 equals -2x, and we divide both sides with -2. We got -5 equal x, so the value of x is -5. Am I correct?
Yes, it's correct.
Okay. So what properties of vector do you use in to solve this problem? The dot
I
product, yeah.
use the dot product. Yes,
Because A is perpendicular with B. It is
yes,
known in question, yeah.
yes, ma'am. There's a question.
Okay. Okay, thank you, Samuel. For the
Thank
others,
you.
maybe any discussion about this problem? Is it clear enough for you? Okay, maybe we can go to the next problem, yeah, to the next question. We have two number remaining. Marsha. Marsha will try to answer number 3. Okay, please, Marsha.
Okay, let me answer number 3. From the exercise, that if U are 331 and V are 221 are sides of parallelogram is square units. So from the problem we got area of parallelogram is U multiplied V. So we got vector U multiplied, vector U times vector V. So we got IGK 331 and 221. And the product are 3121I minus 312IJ plus 33 and 22K. So we got 3 minus 2I minus 3 minus 2J and plus 6 minus 6K. So we got I minus J. From the vector U and times vector V, we got square root from 1 to the power of 2 plus -1 to the power of 2. So that means we got square root of 2.
That's all, Marcia. Okay, how about Marcia?
Yeah, that's all, ma'am.
How about the Marcia answer?
Yeah, it's correct, ma'am.
Okay, are you sure that this is correct?
Yes, ma'am.
Okay, how about the others? Okay, if there is no discussion again, yeah, we continue to the last number. Kalista want to try to solve the problem of number 1, yeah?
Yes, ma'am.
Okay, please go on, Kalista.
Okay. Okay, for the question number 1, if vector u, the component of vector u is 1, 5, -10, and 3, and vector v, the component of vector v is -5, -3, 4, and 7, then the distance between u and v is, since vectors u and v are in a 4-dimensional space, we can use the distance formula between two vectors. So the square, we can use this formula, u1 subtracted from v1 squared and plus u2 subtracted from v2 squared, and so on, and the square root of 1 plus 5 squared, plus 5 plus 3 squared plus -10 subtracted from 4 squared plus 3 subtracted from 7 squared, and we solve that the square root of 6 squared plus 8 squared plus -14 squared plus -4 squared, and the square root of 36 plus 64 plus 196 plus 16, and the value is the square root of 13 and 12, and the approximation is 17.7.
How about the answer? This correct ya? Pakai rumus jarak yang X1 dikurangi apa? Ya, oke. Okay. It's all done ya? It's all done, and maybe before the class will be finished. Do you have any question for me or maybe for the group presentation?
I think it's enough, ma'am.
Okay, if it is enough, maybe for the group, you can closing your presentation.
And so, okay, so
Okay, ma'am, let me
that's
stop my share screen.
okay. Thank you, Kalista. So that's all from us. Group 8 is about Vector. See you on next week. Thank you for all all of you guys for listening us. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh. Okay, thank you. Give applause for the group 8 for the presentation, and we have 2 group remaining for the next meeting. Maybe next week, inshallah. And after that, we will have a final exam. Okay, class. I think for today it is enough. Sorry if there is a false from me, and thank you for your participation today. And assalamualaikum warahmatullahi wabarakatuh.
Thank you, ma'am.